for people who show up late or people who have to leave early to see the video. Any question before I get started with chapter 8? Oh, no question. Let me take a look at this Chinese.
Come on. Look at that. Oh.
Cool. All right. So let's get started off with chapter 8. So let me make sure I'm on chapter 8 on my thing. All right. So let's go ahead and share my screen. All right. So today we should be finishing up chapter 8 and we should be getting on with chapter 9. All right. So we last left off on part A. So in part A, we described the sampling distribution. So for part A, we found mu of p hat, which is just equal to p, which is equal to 0.75, where we're also able to find sigma of p hat, which is the square root of p times 1 minus p divided by n. And when we did the math for that, we got 0.0306. And lastly, using the central limit theorem by checking to see if we have a large sample size. And we were able to do n, which is 200, p, which is 0.75 times 1 minus 0.75. When we did that, pretty much we got 37.5, which is indeed greater than or equal to 10. So we said our distribution was normal. So today what we're gonna go ahead and do, we're gonna go ahead and find the probability. So in order to find the probability, we're gonna use this formula to find the z-score. So we're gonna say z is equal to p hat minus p divided by standard error. So let's go ahead and now we're going to move on to part B. So for part B, it says find the probability of p hat being greater than 0.78. So they're telling me p hat has to be greater than 0.78. So in this case scenario, p hat is equal to 0.78. Okay, so if I do sorry about that. So if I draw 0.78, I'm going to draw to the right-hand side of 0.75. So I know p hat is equal to 0.78. I know p is equal to 0.75. And I know standard error is equal to 0.0306. So I'm going to go ahead and find the z value. So z is equal to p hat, which is 0.78, minus my p, which is 0.75. And you divide that by standard error. Standard error in this case, we found it to be over here, which is 0.0306. Any question? I got 0.78 minus 0.75 divided by 0.0306. All right, so I'm gonna go ahead and move it over to my TI-84 because I just want to calculate this in my TI-84. So let me share the TI-84. Well, let me first bring it up. There we go. All right, so let's try this again. So let's share TI-84. All right, so for this one, what you want to go ahead and do 0.78 minus 0.75. That should give you 0.03. Then you divide it by standard error, which should give you 0.0306. So if you look at my Z value, you get Z is equal to 0.98, and look at, well, you look at 2 decimal places. So we get Z is equal to 0.98. Any question on where did the 0.98 come from? All right, so let's go back to my lecture notes. All right, so there go 0.98. So we converted the 0.78 and we converted it into a Z-score of 0.98. So remember 0.78 and 0.98 are pretty much the same thing. The only thing different, one of them is your p-hat, the other one is the Z value. So if we go back and look at this, if you see it says find the probability that p-hat is greater than 0.78. So which side should I shade of the 0.98? Should I shade the left side or should I shade the right side? Cool. All right, everybody's saying the right side. And by everybody, I mean the 2 people or the 3 people. All right, so we shaded the right side. So now that I have my Z value, I'm gonna go ahead and do normal CDF. So if we go ahead and do normal CDF, all right. So if you look at it, we want to do the lower bound. So the lower bound is the lowest value that gets shaded. Since I found the Z value, I'm gonna prefer to use the Z value versus using 0.78. So if you look at the Z value, it's 0.98, and that's my lower bound. If you look at my upper bound is keep going and going to the right-hand side. So where you say upper bound is 10 to the 10 power. And if you look at this one, since I found my Z value, if you remember, anytime you have the Z value, the mean and standard deviation is automatically 0 and 1. So that means I'm not gonna have to enter 0 and 1. All right, any questions? So far I got normal CDF 0.98, comma, 10 to the 10 power. All right, let's go over to the TI-84 again. And let's go ahead and calculate it. So we'll do second, vars, we'll do normal CDF. So I'll do 0.98. I'll do 10 to the 10 power, which I already have here. I'll do mu is 0, standard deviation 1, because remember we have the Z value. So we go calculate, and that's our answer. So we get 0.1635. Cool. And that's how you find the probability for a distribution that you're doing proportional data set for. All right. Any question for that first problem? All right. So remember, this is if we find Z. So that's how you want to do it if you find the Z value. But if you kind of remember for 8.1, you can also do this if you just have p hat. So we'll do if we use, so we'll say normal. So we'll do normal CDF. And for this one, we're going to use our p hat. So our p hat in this case is 0.78. And if you look at it, it's still going to positive infinity. So that still stays the same. But what is going to change is our mean and our standard deviation. Because if I don't want to find the Z-score, you have to tell them what was the mean and what was the standard deviation for p hat. So if you look at the mean was 0.75. And the standard deviation, which is your standard error, which we found over here, was 0.0306. So if you don't want to find the z-score, this is the other way that you could do it. So you could put p hat, and then put the upper bound, and then put the mu of p hat, and you put sigma of p hat. So I'm going to go ahead and I'm going to find this in my calculator. For that way I could show you get the same answer, or roughly the same answer. So you go second vars, do normal CDF. So you go 0.78. Yeah, there you go. You scroll down. So for mu, you put 0.75. Sigma, you do 0.0306. And then you go over here and paste. Go to enter. And if you look at it, you roughly get the same answer. You're off by a little bit just because essentially rounding off error. But you get the same thing. So no matter which one you use, you should still get the same answer. Any question for the last problem? All right, so let's do C. All right, so for part C, yeah. Yeah, on the test, both of them will be correct. For this one, since I know, depending like on how many decimal places you use, you might be off by a little bit. So for these questions, I actually set a margin of error. So I'm gonna set like a margin of error like 1,000. So that way it should be correct either way you do it. So I will set a margin of error for this one. Yeah, no problem. All right, cool. All right, so let's do part C. So for part C, we already know mu p hat equal to 0.75. We know sigma p hat 0.0306. So what do you want to do? Do you want to find the probability, find the z-score, or do you just want to go straight into normal CDF? So z-score or CDF, which one do you want to do? All right, go straight into CDF. So first we're gonna do 0.63. 0.63 is to the left of 0.75. So if you look at this one, it's pointing to the left-hand side. So this is pointing to the left-hand side, that means we shade the left-hand side. So since you requested straight into normal CDF, we're gonna go straight into normal CDF. So for this one, you first want to find the lower bound. So the lower bound is the lowest value that possibly could get chosen. If you look at this one, since there is no kind of like cutoff for the lower number, your lower bound keep going to negative infinity. So we put negative 10 to the 10 power. If you look at the upper bound will be what? Cool, 0.63, good job. And then remember, for this one, since you didn't find the z-score, you had to tell it mu of p hat and sigma of p hat. So you put 0.75 and you put 0.0306. So then what I'm going to go ahead and do, I'm going to go ahead and enter this into TI-84, and that will be it for that problem. So we go to second, we go to vars, we go to normal CDF. So we say, negative 10 to the 10 power. Then for upper, we say 0.63. Then for the lower, for mu p hat is 0.75. And then for sigma p hat, well, 0.0306. Okay, press enter. All right. So you get 4.4 e -5. All right. So you get 4.4 e to the -5. So on the test, you should never put that your final answer is 4.4. Like as soon as you put 4.4 for a probability, you should kind of already know that's not the correct answer because remember your probability can never be higher than 1. So usually if you see a number bigger than 1, that's because you have to look at the end of it. So you want to look at this because it says e to the -5. So the e to the -5 is telling you it in scientific notation. So you have to get the decimal and move it 5 spaces to the left. There you go. 1, 2, 3, 4, 5. There you get 0, 0, 0, 0. So for this answer, you get 0.000044. And that's it for C. So it's kind of telling you like the probability that it's less than 0.63 is essentially impossible for it to occur because if you look at it, the probability is not even 1%, it's less than 1%. All right, but that's it for C. Everybody good for C? All right, so that was kind of like a warm up. So right now we're gonna do a word problem. All right, so for this one, I'm gonna make a modification. So instead of putting of the population, we're gonna change that and we're gonna change that of American. So change this to American. So we're gonna change that from of a population to American. So it'll say, according to the Bureau of Labor Statistics, 5% of Americans surveyed were unemployed at the end of 2019. All right, so for this one, what does the 5% represent? So the 5% represents my population size. If that was sample was a little bit like 10, 20, 30, 40, 50, not a 5%. Cool. That's a mini guess. P. So the 5% represent RP because they're telling you 5% of Americans were unemployed at the end of 2019. All right. So that's pretty much everything that was given to us in A. So for A, it says describe the sampling distribution of p hat for a random sample of 250 people. So for this one, what's my sample for part A? How many people did it say we sample? So that's our sample. All right. So for this one, what we're gonna do, if you look at it, it says describe your sampling distribution. So for this one, we're gonna find mu of p hat. We're gonna find sigma of p hat. We're also gonna check to see if our data set could be, we'll say, so we're gonna check to see if our distribution is approximately normal or is it normal or is it not normal? And we're going to check the central limit there to see if we have a big population. And we also want to check to see if we have a large sample size. Okay. All right, so I'll give you a minute in case you're writing that down. All right. So for this one, what would be my mu of p hat? Like, what should I say mu of p hat is equal to? Yeah, cool. 0.05, perfect. So P is 0.05. So then we're going to find sigma P hat. So that's 0.05 times 1 minus 0.05. And we divide this by n, which is 250. So let's go ahead and use our TI-84. And we'll use our TI-84 to calculate this. So say square root, oops, gotta turn it on. Square root of 0.05. So for this one, I'm gonna multiply by 1 minus 0.05. 1 minus 0.05 is 0.95. It's just easier to do that. And then divide it by 250. So if you do that, all right. So that's what I get for sigma p hat. I get 0.0138. Any questions so far how I got that? Okay, so now what we're gonna go ahead and do, we're gonna go ahead and check to see is, for this problem, do they tell us our distribution is normal? Cool. So they don't tell us our distribution is normal. So since they don't tell us our distribution is normal, what we have to do, we're gonna have to use our central limit there to be able to see if we could say our distribution is approximately normal. So let me go ahead and switch over to my notes. So we already know it can't be normal. So it's either gonna be approximately normal or it's gonna be not normal. All right, so the first thing we're gonna go ahead and check to see, we're gonna check to see if we have a large sample size. So we're gonna do n times p times 1 minus p, and this value should be greater than or equal to 10. If it's smaller than 10, that means we don't have a large sample size, and that means it's not approximately normal. So for this one, we're gonna say 250 times 0.05 times 1 minus 0.05, and let's see what does that get us. So I'm going to do this in my calculator. So we do 250 times 0.05 times 0.95. So if you multiply those three numbers together, what do we get? Oh, thanks. So you get 11.875, which if you look at 11.875, is actually bigger than 10. So we could say we have a large sample size. So now what we have to do, we have to check to see if we have a big population. So if you remember for big population, you get 20 multiplied by n, and this should be bigger than your population size. So let's do 20 and let's multiply by n. So we're gonna do 20 multiplied by n, which is 250. So what's 20 multiplied by 250? Yeah, so you get 5,000, good. All right, so that's 20 multiplied by 250, which you get 5,000. So now you kind of want to ask yourself, is there more than 5,000 American in general? Or are there less than 5,000 American? Cool, yes. There should be more than 5,000 American. So since our population is indeed bigger than that, pretty much our central limit theorem checks out. So now we can say is approximately normal. And that's how you check the big population. You have to do 20 multiplied by n. And then you kind of have to ask yourself, okay, is there more? Well, is the population bigger than this number? If the answer comes out to be no, then you go ahead and say the central limit theorem does pass. All right, but that's it for that. Any question on how we describe our sampling distribution? All right, so no. All right, so let's go ahead and find the probability. So for this one says in a sample, a random sample of 200 people, what is the probability that 17 or fewer people are unemployed? All right, so for this one, it should say 0.05. So if you look at this one, yes, it has to pass both of them in order for it to be approximately normal. If one or both of them fail, then we cannot say it's approximately normal. All right, so let's go ahead and do B. So it said if a random sample is 200 people, if a random sample 200 people, what is the probability that 17 or fewer people are unemployed? So they're not giving us p hat, but they're giving us the information to find p hat. Because we know this is n, and this is our x. Because remember, x is the characteristic that we're looking for. So right now we're looking for people who are unemployed. So to find p hat, we have to do x divided by n, where x is 17, n is 250. So I'm going to go ahead and do 17 divided by 250. But any question on how I got 17 divided by 250? All right. So if you do 17 divided by 250, you actually get 0.068. So if you look at 0.068, should fall somewhere over here. And which side of the points? 0.068. Which side of the 0.068 should I shade? Should I shade the left side or should I shade the right side? Cool. So you shade the left side. All right, so let's go ahead and do this. So I'm assuming you just want to jump right into normal CDF to find the answer. So let's do normal CDF. So we'll say normal CDF. All right, so for this one, what's my lower bound? Negative 10 to the 10 power. What's my upper bound? Very good. What's my mu of p hat? There you go. And lastly, what's my sigma of p hat? All right. Any question on how I enter this so far? All right, so what I'm gonna go ahead and do, I'm gonna go ahead and do this on my TI-84, and that will be our answer for this one. 10 to the power, 1068, 105, 10138. So if you do this on your calculator, you should get 0.9039. Any question? I got 0.9039. All right, so what I want you to go ahead and do, I want you to go ahead and practice on part C. So practice on part C. And once you finish with part C, what I want you to do, yes, what do you call it? Send me a private message or you put it on the chat board, put your answer, and that way I can let you know if you got it correct or if you still need a little bit of help. But try doing this one on your own. So right now, let's try doing this one. You might want to check to see your lower bound, your upper bound might be mixed up. So you might want to switch your lower bound with your upper bound, your upper bound with your lower bound. Yeah, no problem. All right, so let's try doing that one. Ooh, no. All right, so let's try doing this one. A lot of you are having trouble with this one. Well, not a lot of you. 40% of you. All right, 36% of you now. All right, so it said in a random sample of 250 people, what is the probability that at least 7% are unemployed? So if you look right here, they're actually giving me p hat now. Because if you look at the one previously, they told me how many of the 250 people are unemployed. So they told me 17 out of the 250 are unemployed. But if you look at C, they're telling me of the 250 people, 7% or at least 7% are unemployed. They do have to pay attention to this one because they could give it to you as an X or they could give it to you as a probability. But you should be able to tell the difference between a probability and an X. Because if you look at the X, well, they don't tell you that 17% or anything like that. But if you look at 7, it says 7%. So you do kind of want to make some mental notes on the difference of the two. All right, so let's go ahead and let's look at this. So we have 7%. So here you go 0.05. Here you go 0.07. So some of you might be getting hung up with this again, at least. So remember, at least means that's the minimum, but it could be higher than that value. So it could be anything bigger than 0.07. So since it says at least, it means you get 0.07 and you shade everything to the right-hand side. All right, any questions so far in regard to that? All right, so then what you want to go ahead and do, we want to go ahead and do normal CDF. So we'll say normal CDF. So if you look at the lower bound is equal to 0.07. My upper bound is going all the way to the right-hand side, so going to infinity. Then if you look at mu, well, it's the same thing as this one, 0.05. And my sigma does the same thing, 0.0138. All right, any question in regard to any of those inputs? All right, so let me go ahead and enter them. So we get 0.07, comma, 10 to the 10 power, comma, 0.05, comma, 0.013a, close parenthesis. Right. So if you enter this into your calculator, you should have gotten the correct answer of 0.0736, and that's it. So that's what your answer for C. So hopefully if you didn't get it correct, now you can see why you didn't get it correct, and now you know how to get the correct answer. But any follow-up question in regard to part C? All right, so let's go ahead and move on to the last problem of this section. Yeah, if they give you the probability, that's your p hat. All right, so let's do this. So it says, suppose that 47% of all adult women think they do not get enough time for themselves. A opinion poll interviewed 1,025 randomly chosen women and record the sample proportion who feel they don't get enough time for themselves. So right here, what's my sample? Perfect. N is 1025. All right, what is this 47? What does it represent? Cool. All right, so we got 2 that says P, 1 that says P hat. So if you look right here, it says all So it says all adult women. So it's saying all women. So it's saying all women. That's your P. Because if you remember P is your population proportion. P hat is your sample proportion. So since it's telling us all women feel like they don't get enough time for themselves, that means that should be considered your P, not your P hat. In this case scenario, who's my population? And this is going back to chapter 1. Perfecto. Adult women. Oh, that's ugly, yeah. All right, so that's my population. All right, everybody good so far on all of my notations? All right. So if you look at the problem, it asks us for part A to describe the sampling distribution of P hat. So what we want to do, we want to find mu of P hat. We want to find sigma of P hat. We also want to say if the distribution, we want to say if it's normal, not normal, or if it's approximately normal. So to be able to tell if it's one of those three, what we have to do, we have to check the central limit theorem. And we have to check for big population. So we'll say big pop. And we also have to check it for large sample size. Cool. And just remember the formula for these are 20 times n has to be smaller than capital N. And large sample size is n times p times 1 minus p is greater than or equal to 10. All right, so let's do the easy one. What's my mu of p hat? Cool. 0.47. So that's my mu p hat, and mu p hat is equal to p. So we're going to do sigma p hat, which is 0.47 times 1 minus 0.47, all divided by n, where n is 200. Oh, sorry, that was the last problem. It's 1,025. So let's go ahead and do this on not COSCOM, on the TI-84. So let me turn it on. So we go second square root. We do 0.47 multiply. I'm not going to do 1 minus 0.47. I'm just going to computate that, which is 0.53, all divided by n, where n is 1,025. And for this one, you should always get 4 decimal places. Like that's the minimum decimal places you should get for standard error. It should always be 4 decimal places for this one. So if you look at it, you get 0.01558. But if you look at it, since I'm getting 4 decimal places and the number in the 4th place is 5, I have to use the 8 to see if I should round it up. So since 8 is bigger than or equal to 5, you round up this 5. So we should get 0.0156. So that's what you're going to put for standard error. Any question how you got 0.0156 for standard error? All right, so let me switch back to my notes. The notes. All right. So All right, so if you look right here, I got mu p hat is equal to 0.47. I have sigma p hat is equal to 0.0156. So now we have to check to see if my distribution is normal, not normal, or approximately normal. So for this one, can I say my distribution is normal? Cool, no. So we're not gonna say it's normal. The reason I'm gonna say it's not not that it's not normal. The reason why we can't choose normal, because if you look at the problem doesn't state that it's normal. So it's either gonna be non-normal or approximately normal. So that's where the central limit theorem come into play. So I'm first gonna check to see if we have a big enough sample size. So for a big enough sample size, we're gonna have to say n times p times 1 minus p, and we have to see if that's bigger than 10. So we do 1025 times 0.47 times 1 minus 0.47. So I'm actually going to do that in my calculator. So 1025 multiplied by 0.47 multiplied by 0.53. All right. So you get 255.3. So if you look at, I get 255.33, and 255 is bigger than 10. So we could say we have a large sample size. Up next, we're gonna say if we could say we have a big population. So let's go ahead and see if we can say if there's a big population. So we do 20 times 1025. So if we do 20 times 1025, you get 20,500. So you get 20,500. So now you have to kind of think, and you have to go like, is there more than 20,500 adult women? So yeah, so the answer for that should be yes. There's way more than 20,500 adult women. So since we have a big population, and since we have a large sample size, the central limit theorem condition have been pretty much worked. And we could say that our distribution is approximately normal. And that will be it for part A. Everybody good for part A? Yeah, sure. Yeah, you're just using logic for the population. Like, usually, like, if it's a population that's kind of like widely known, like, you should just use logic. If it's a population that you don't know, I'll try to put the population there for you. But you're just using logic. Like, if I tell you, like, the population of dogs, like, you should know the population of dogs are probably like in the millions and stuff like that. So just use logic for that. All right, so somebody wanted me to do this one on the calculator because their answer was slightly different than my answer. So we do 1,025. You multiply this by 0.47. And then if you want, you could do parenthesis 1 minus 0.47. Close the parenthesis, press enter. Also, like, kind of like, you really don't want to do 1 minus 0.47 there. All you do in the calculator first and go like, hey, 1 minus 0.47 is 0.53. And then you go 1025 times 0.47 times 0.53. And then say equal and la di da. You get the same answer. Yeah, so if you don't like using parentheses, or if you're not good at using parentheses, always calculate the 1 minus part first. So that way it'll be easier yet to enter it into the calculator. All right. All right. So let's go to part B. Or is there any other question in regard to part A? All right, so for part B, so what is the probability that the poll get a sample in which fewer than 45% say they did not get enough time for themselves? All right, so remember, what does a 45% represent? Does that represent X or does that represent P hat? Yeah, so that represent P hat. Like an easy way to know that represent P hat, it has a percentage. Anytime it has a percentage, it represents P hat. It's impossible for it to represent X. So that should be P hat. So what do you say? P hat is equal to 0.45. All right, so for this one, there's a little typo. I put 0.45 right here. That should say 0.47. So if you can, yes, erase that typo. And then right here, you put 0.47. So here go P hat, which is 0.45, which is to the left of 0.47. So we'll put 0.45. So for this one, what we want to go ahead and do, we want to go ahead and decide which side of 0.45 should I shade. Should I shade the left side or should I shade the right side? So which side should I shade? Perfect. All right. And for this one, like if you're looking for a keyword, the keyword here is fewer than. Because fewer than means it should be smaller than 45. So Q the left side. La, 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 la. All right. Everybody good on this shading? All right. So let's go ahead and do our normal CDF. All right. So for this one, what's my lower bound? -10 to the 10 power. What's my upper bound? What's my mean? And lastly, what should I put for standard deviation? Wait, 0.0156. And you close that parenthesis. Here, let me double check that. Yeah, there we go. Cool. All right, so I'm going to go to the TI-84. I'm going to enter this, and we're going to be all done with chapter 8. And then we could go on to chapter 9. 9. All right, so we go second, we go VARs, we go normal CDF. So right here, lower bound, -10 to the 10 power. Well, that's already there, so I'm going to leave it there. Then you go 0.45. Then you say 0.47. And after you enter sigma, which is 0.0156. So my lower bound is -infinity, my upper bound is 0.45, my mu is 0.47, sigma 0.0156. Go here and paste to paste. If you look at it, so you should get 0.0999. Yeah, and that's 4 decimal places. So you get 0.0999. Any question on how I punched it in before I go back to my notes? No, for this case, we wouldn't round to 1 because if you actually look at what I got on my calculator, I got 0.0999. Because you do for probability, you want to keep it to 4 decimal places. If the number next to the 9 would have been like a 5, 6, 7, then you round it all off, and then you would have said 0.1. But for this one, since it's 0.09991, since that 1 isn't bigger than 5, that's why it should be 0.0999. No problem. All right, so if you look at this one, it's telling me like the likelihood if we randomly select, how many people are randomly selected? All right. Cool. All right. So for this one saying, if I randomly select 1,025 adult women, the probability that 45% of them or less say they don't have enough time for themselves is approximately like 10%. So they're telling you there's a 10% chance that that will happen. So you're saying if we randomly select 1,025 adult women, the probability that 45% of them or less, well, sorry, 47% of them or less, uh, sorry about this. So the probability that less than 45% of them will say that they have less time for themselves or they don't have enough time for themselves, there's only a 10% chance of that happening. So it's kind of telling you it could happen, but it's more likely that you get a number bigger than 45%. All right, but that's it for that. Any question in regard to that last problem? All right. So up next, we're going to go over to chapter 9. So for chapter 9, you are going to need 2 tables that I put on Canvas. So let me show you where to get those 2 tables in case you haven't seen those 2 tables. Go. So you just want to go to the home page and you'll find it here. So if you go to home page, if you look where it says tutor schedule and net tutor, you have table. So T table, you're going to need this table for 9.2. Chi-square table, you're going to need it for 9.3. So all you have to do, you click it. So if you want, you can just download it and you just have it on your tablet or on your phone or something like that. Or if you have a printer or if you have access to a printer, you just print this out for that way you could just have it handy right next to you. So you do want to get the T table. The T table is 1 page long. Same thing for the chi-square table. The chi-square table, no, you don't want to meet up. The chi-square table is also 1 page long. So yeah. So if you have a printer, print them out for that way you don't have to be like navigating through everything to get it. But if you don't have a printer, just make sure that you haven't downloaded it so that way you already have them with you for that way for a test or for a quiz, you could have them handy with you. All right. Any question where to find the tables? All right, everybody know what the table are at. All right, so let's go to chapter 9. So let me download chapter 9. Las notas. All right. Yeah, they should be in your book as well. It might be a little bit different than the one I got, but it should be relatively the same. All right, so we're gonna start with chapter 9. So chapter 9 is confidence interval. So for a confidence interval, the way that you want to think about confidence interval, so if you look at the word interval, interval means you have a range. So whenever we find a confidence interval, we're gonna have a lower number, and then you're gonna have an upper number. So when we find a confidence interval, we're gonna find an interval. So what we're hoping for that confidence interval that we find, we're hoping that it contain my parameter. So we say the confidence interval should contain the parameter. So we're hoping that the confidence interval should contain the parameter. So the way that you kind of want to think about it, we don't know what the parameter is, and we're hoping that our confidence interval kind of narrows it down to what it possibly could be. So if in case you forgot what parameter means, parameter is going back to chapter 1. Parameter mean a numerical value that I extract from the population. So in this chapter, we're going to be focusing on 3 parameters. Here, let me see. Okay. So the first parameter we're going to be focusing on is the population proportion. So that's going to be the first parameter we're focusing on, the population proportion. The second parameter we're going to be focusing on is mu. And then the very last parameter we're going to be focusing on is sigma. So kind of think about it. We don't know what the parameter is, but our confidence interval should help us find what the parameter should be. So it's not going to exactly tell us the exact parameter, but it should tell us the range that our parameter should be in. So it should tell us the parameter is between 1 to 5, or the parameter is between 20 to 25, something like that. Yeah. Any question in regard to that so far? Okay, so what we're gonna do, we're gonna see a simulation right now. And I'm hoping that this simulation should help you out with what the confidence interval is trying to do. So let's say Rosman. Here's the Jesus. Perfect. All right. So let's imagine this. So let's imagine, where's the chat? All right. So I'm gonna set up a scenario. So assume we are aliens. All right. So let's assume that we're aliens and we find a coin. So we find the coin and we're aliens. So we don't really know that the coin should be, hey, half of it should land on head, the other half should land on tail. We don't know that because we're alien. So if I don't know like what percentage of the time it will land on head or tail, how can I test that? Cool. So we could do an experiment. So we could do an experiment on flipping this coin. How many times do you think we should flip this coin? So you want to flip the coin 100 times? Here, let's flip the coin 10. We'll flip it 10 times. I don't think the alien have enough time to flip it 100 times. So we'll flip it 10 times. But do you think if we flip it 10 times, like whatever it lands on, if it lands on like 60% heads, 40% heads, 40% tail, like am I absolutely gonna trust that? No. So let's go ahead and let's do our sample. So we'll do our sample. All right. So if you look right here, here, you can't see where I'm pointing at right now, but let me get the spotlight. All right. Can everybody see like a spotlight right now? Cool. So if you look right here it says I flipped it and 50% of the time it landed on one side, 50% of the time it landed on the other side. So if you look right here, like we can't just trust our data set because we know this is an experiment. So we know it might be off. Like we know it's not gonna be exactly 50%, but it should be close to 50%. So do you see this green line over here? All right, everybody see this green line. So what I'm gonna do, I'm gonna click on this green line. So if you look at the green line telling me it could be anywhere from 0.190 all the way to 0.810. So if you look at it, it gave me this confidence interval. So it gave me this confidence interval based off of this sample. Because I know this sample is not going to be 100% accurate. But if you look at it, it could be accurate, but I have to kind of give it like a little wiggle room. So I'm not going to trust that it's going to be exactly 50%, but if you look at it, we gave it some wiggle room where we added and we subtracted. If you look at it, the added and subtracted 31% or 0.31, and we'll call that wiggle room. So this is what we call a confidence interval. But do you think it would be fair yet to do one experiment? Or would we want to do this experiment like many, many times over? Cool. All right, so let's do this experiment again. So I'm going to go again. Cool. Oh, wait, let me see. This is not secure. All right, so let's do this again. All right, so if you look now, all right, now, so let's say failure is head, let's say tail is success. So how many times did it land on tail this time? So remember, failure is head, success is tail. So how many times did it land on? Yeah, good, tail. So 70%. So if you look at this experiment now I got 70% tail, 30% heads. But let's look at the confidence interval. Because remember, we're not going to trust this experiment because we want to give it some wiggle room because the wiggle room is our confidence interval. So let's see our wiggle room. So if you look at it, it gave us a confidence interval of 0.416 all the way to 0.98, and it got kind of cut off. So that's our confidence interval. All right. So if you kind of look at it, pretty much what the confidence interval trying to do, it's trying to get us a range, and we're hoping that the parameter that we're looking for fall within that range. but you kind of know the parameter is not always going to fall in that range because sometimes the information that we have is not a valid sample. Because say if we get a sample and that sample is all tail, like that's going to give us a wrong confidence interval and that's going to give us to a misleading diagnosis. So you can't always trust one sample. So that way we always do this multiple times. All right, so let's kind of play around with this. So when we do a confidence interval, it's not meant for one time or two times. You want to do this many times. So what I'm going to do, I'm going to say, hey, let's do this 100 times. So let's do this 100 times with a sample of 10. All right. So what type of line do we see? So we see green line, but we also see what type of line? Cool. So we also see red line. So what do you notice about the red line? Why do you think they're red and not green? Well, they're not outlier, but what's going on with them? Like, look at the green and look at the red. Like, what do the red have in common compared to the green? Well, yes, the red, we do have fewer red than green. But like, what do you notice about the red? What make them red? Like, why do they choose these to be red versus choosing the other one to be green? Well, they're farther away from the center, but if you look at it, they completely miss the center. Because if you look at this one right here, it doesn't touch the center. If you look at this one right here, it doesn't touch the center. If you look at this one, it doesn't touch the center. So if you remember, we're doing the confidence interval to capture the parameter. So these red ones are all the one that missed the parameter, because the parameter is this vertical line right here. Because theoretically, when you flip a coin, the coin should land 50% on tails, 50% on heads. So these red ones completely missed this line right here. So that's why they're red. So they're telling us these did not capture the parameter. The green one did capture the parameter. All right, so how many red do we have? Cool, 7. So if we have 7 red and I did this 100 times, how many green do we have? Cool, 93. So the way the green and the red work, it depends on your confidence interval. So if you look at my confidence level right here, what did I put my confidence level to be? Cool, 95%. So when we do the 95% confidence level, or when we do any type of confidence level, that dictates if I repeat this experiment many times, what percentage of the experiment is gonna fail and what percentage of the experiment is gonna succeed. So if you look at it, since they have a 95% confidence level, it's telling me that roughly 95% of the time it's gonna be correct. The other 5% of the time it's gonna be incorrect. But just remember, just like with anything, it's not exactly that. That's why for this one we got 93 green and 7 red, because the 95% is not always gonna be 95%, but it should be close to 95%. All right, everybody kind of go with the confidence level? All right, I'll take okay. All right. So let's mess around with the confidence level. So say if I want a lower confidence level. All right, what confidence level do you want? So you tell me. If I want a lower confidence level, how low do you want it to go? Ooh, we're going 75. All right, so we're going 75% confidence level. All right, we'll do 25% after 75%. All right, so what do you think is gonna happen with these lines? Do you think I'm gonna get more green line or am I gonna get more red line? All right, cool. So we say more red. What do you think is going to happen with these intervals? Do you think they're going to get wider or do you think they're going to get narrower? All right, so let's go ahead and let's check it out. So I'm going to go sample. All right. So what happened to the red? Did I get more red or less red? Yeah, if you look at it, I actually got more red because that kind of makes sense. Since I lower my confidence level, that means I'm less confident. So that means our experiment gonna be less accurate. But also, what happened to my interval? Did it get wider or did it get narrower? It got narrower. So actually, when you lower the confidence level, your confidence interval actually get narrower and narrower. Kind of think about it. When are you more confident? If we have a big interval or if we have a small interval. So if I have an interval from like 0.20 to 0.80, or if I have an interval from 0.50 to 0.55, like I'm more confident in 0.20 to 0.80 because I have more room for error versus 0.50 to 0.55. You actually have less room for error. So you're not that confident with that one. So let's mess around with this and let's make this into 25%. So if I make this to 25%, what should happen with my interval? Should it get wider or should it get narrower? All right, so let's find this. Ooh. All right, so if you look at it, it actually did get narrower because now we're even less confident. Since we're even less confident, it actually got narrower. All right, but for this one, why wouldn't I just always do 100%? Like, why leave any room for error? Why not just always do 100%? Like, if you look at that, that's gonna be always correct. It's always correct. Like, why wouldn't I just always want to be correct? Like, what's wrong with this picture though? Because if you look at the interval, it's going from which number to which number? Yeah, so it's going from 0 to 1. But like, if I tell you, okay, what's the probability that the coin will land on heads, and you tell me it will be anywhere from 0% to 100%, like, wouldn't you go like, no, duh? Like, I already knew that. Like, I'm trying to get a more narrower. Like, I'm not trying to get a bigger range. So that why doing 100% kind of useless because it's gonna give you a bigger. It's gonna tell you it's from 0 to 100%. So 0 to 100% and nothing like that spectacular. Because if I tell you anything has a 0 to 1% chance or 100% chance of occurring, like you just look at me going like, I already knew that was gonna happen. So that way we never do 100% or 100% confidence level. All right, so let's reset this. Okay. So let's do 95%. All right, so let's go recalculate. So here we're back to our 95%. So let's go to the sample size. So if you look right now, do you think our sample size is pretty big or is it pretty small? Yeah, we'll probably have a pretty small sample size. So let's increase it. Let's increase it to 100. So which one would you trust more? A sample size of 10 or a sample size of 100? So will you trust somebody who flipped a coin 10 times or will you trust somebody who flipped a coin 100 times? Yeah, so you'll probably trust the person who flipped a coin 100 times because you're going like he has more data set. So whose data set will be more accurate? The one with 10 sample size or the one with 100 sample size? So probably the one with the 100 sample size. So what do you think is going to happen with these intervals? If they become more accurate, would they become more accurate if they get wider? Or would they become more accurate if they get narrower? Yeah. So for this one, they're more accurate than narrower because remember, we're trying to find the parameter. So if we get a narrower confidence interval, that's better for us because if I tell you the parameter can be anywhere from 0.48 to 0.52 versus telling you it's from like 0.40 to 0.60, I'd much rather have 0.48 to 0.52 because that's more accurate and you're narrowing it down. So let's go ahead and let's do another sample of 100. And I want you to get to kind of focus on the shape of the interval if you get wider or narrower. So let's do that. Cool. All right, so if you look at it, it indeed got narrower because essentially the bigger your sample size is, the more accurate it's gonna be. So if I were to increase this to like 1,000, it will even become more narrower. Because the bigger your sample size is, the more trustworthy your sample size is, and the more accurate your sample size will be. All right, I think that's it for this thing. Any question in regard to this simulation? All right, sweet. All right, so we get to go back to chapter 9 and we get to start doing some math. All right, so up next, we're gonna get to 9.1. So 9.1, we're gonna obtain a point estimate for the population proportion. So let me do something to my screen because there's a bunch of screen. Okay. So we're gonna get a point of estimate for the population proportion. So in this case, for 9.1, we don't have population proportion. So I don't know what the population proportion is. We're gonna use a confidence interval to estimate that. So if I don't know the population proportion, I want something to estimate the population proportion. So that way we have something called a point of estimate. So if I don't know what the population proportion is, what we're gonna do, we're gonna use p hat to estimate what the population proportion is. Because if we don't know what the population proportion is, the best estimate for that is the p hat. Any question in regard to p hat and why we call it the point estimate? All right. So let's do our very first example on calculating point of estimate. So for this first example, it says in July 2018, a university poll asked 1,783 registered voters nationwide whether they favor or oppose the death penalty for a person convicted of murder. 1,123 were in favor. Obtain a point of estimate for the proportion of registered voters nationwide who are in favor of the death penalty for a person convicted of murder. All right. So what's my sample? So how big of a sample size do I have? Good. So we got 1,783. So these are my registered voter. All right. So let's find our X. So for our point of estimate, for the point of estimate, are we focusing on people who are in favor of the death penalty or people who are opposed to the death penalty? Like, who do we want to find the point of estimate for? So we want to find it for people who are in favor. And Stephanie already gave me the answer for that. So we have 1,200, oops, 1,123 people who are in favor of the death penalty. So if I want to find the point of estimate, all we have to do is divide that. So we go P hat is equal to 1,123, all divided by 1,783. So let's go ahead and do that. So 1,123 divided by 1,783, and you get 0.6298. Right. And we're all done for that. Any question in regard to that point of estimate? Right. So if you kind of remember, I was calling something the wiggle room. So pretty much whenever we got our p hat for the last problem, like whenever we got the proportion of success and proportion of tell, it was like 50%, and then it would have this confidence interval, and then I would tell you, this is how much of a wiggle room we have. So the technical term for this chapter, we call that wiggle room. We call this the margin of error. Yeah. And if you kind of like pay attention to that word, margin of error, it's kind of telling you like how much room for error we have. So it's not telling us our point of estimate has to be exactly correct, because we have our margin of error, and our margin of error telling us like, okay, our point of estimate is this, but we don't have to be 100% accurate with the point of estimate because we're going to give you a margin of error. So kind of like say for the quiz question, if I tell you you have to give me the exact answer, essentially you have no margin of error. But if I tell you have a margin of error of 0.100%, then that's telling me your number or your answer doesn't have to be exactly correct because there is some wiggle room for you. So that's what the margin of error is telling us. And it's telling us how much leeway or how much wiggle room are we giving ourselves to be able to find this. So you kind of know your margin of error, it will depend on the confidence level. It will depend on your sample size. And it also depend on your standard deviation of the population. So all of those factors go into what your margin of error is going to be. You could kind of think about it, if we have like a low confidence level, that means our margin of error is going to be low. Or if we have a small sample size, that means your margin of error will be small. Or if your standard deviation is small, your margin of error will also be small. But if I have a huge confidence level, or if I have a big sample size, or if I have a standard deviation big, then that kind of gonna make my margin of error bigger. All right. Everybody somewhat good with that? All right, so let's get into the formula. All right, so first thing we have to do, we're gonna find something called a critical value. So the critical value is the same thing as your z-value. So for the z-value, we're gonna be using inverse norm to find this. So in order to find the critical value, we're gonna be using inverse norm to find it. And technically what we're going to be doing inverse norm of alpha divided by 2. And that's how you're going to get the critical value. All right, so once you get your critical value, we're going to get our E. E is margin of error. Let me write that down here for you. So we're gonna get the margin of error. So this is gonna be your wiggle room. So there's gonna be like, how much wiggle room do we have? So if you notice, you're gonna get Z, which you're gonna find here, and you're gonna multiply this by standard error. The only thing that's gonna happen, if you look at the formula for chapter 8, and if you look at the formula that I have here for standard error, you should kind of notice it's slightly different. The reason why it's slightly different, if you look at the formula we use for chapter 8, we use this formula of P times 1 minus P divided by N. But if you look at the formula that we're using for chapter 9, it's square root of P hat times 1 minus P hat divided by N. So if you remember in chapter 8, we knew what population proportion was, but in chapter 9, we don't know the population proportion anymore because that's what we're trying to estimate. So since we don't know what the population proportion is, we're substituting P with P hat. So that's the little change that's occurring. And the reason why is because we don't know what P is. So we're going to use the estimate for it, which will be the P hat. Any question for margin of error? All right. So once you find margin of error, you want to find your point of estimate. So if point of estimate is not given to you, you do x divided by n. And then lastly, you want to do the point estimate and you want to add it and subtract it to the margin of error. So if you look right here, it says plus or minus. So that means you want to do p hat minus margin of error, and you want to do p hat plus margin of error. So that's what the plus or minus mean. It just means you're going to do the operation twice. One of them when you subtract margin of error, the other one when you add margin of error. All right, but that's your formula. Any question for that formula? All right. So what we're gonna do a very basic formula, and we're gonna do this one. So we want to construct a confidence interval of the population proportion at the given level of confidence. So we get x is equal to 120, we get n is equal to 500, and we get a confidence level of 99%. So for this one, let's go ahead and do it. So the first thing we're gonna do, we're gonna find z alpha divided by 2. So before we find z alpha divided by 2, we first have to find alpha. So the formula for alpha is this. Alpha is equal to 1 minus confidence level. So for this problem, what do I tell you the confidence level is equal to? Good. You even put it in percent form. All right, so we do 1 minus 0.99. Right. So if you do 1 minus 0.99, what's 1 minus 0.99? Good, 0.01. All right, so if you look right here, that's my alpha. So we're gonna do z of 0.01 divided by 2. So what 0.01 divided by 2? Well, that's z of 0.005. All right. Any questions so far for that math? Okay, so now what I want you to do, now this is where we're gonna do the inverse norm. So let me do a different color just for it could pop. So we do inverse norm. And let's see if you were paying attention. What should I put the area equal to? Not that. There you go, 0.005. Because remember, if you remember over here, I said inverse norm, the area gonna be alpha divided by 2. So once you find alpha divided by 2, that's what you're gonna take inverse norm of. So you put like a little mental note right there or put a little sticky on it. For that way you can memorize that. Or for that way you won't forget that. All right, so I'm gonna go ahead and do inverse norm of 0.005. So let's do second, bars. Let's do inverse norm. So I'm gonna say 0.005. Go enter, enter, enter. We'll say paste. Ooh, what was that? So if you look at it, and for this one, we're gonna get 3 decimal places. So we're gonna say, this give us negative 2.576. All right. Everybody see how to get negative 2.576? All right. So I'm gonna go ahead and transfer back to my notes. All right. So for this z value should always be positive. So even though the inverse norm is always going to give you a negative value, for this z value, it should always be positive. And I'll kind of show you why it should always be positive a little bit later on. But for right now, you kind of take my word for it. This should always be positive. So if this gives you a negative, well, this inverse is always going to give you a negative. So this z value right here always, always, always will be a positive. All right. So up next, I'm going to go ahead and find p hat. So for p hat, if you look at it, it's x divided by n. So x is 120. And then you get n. N is 500. So let's do 120 divided by 500. 120 divided by 500. Cool. What do we get? There you go. 0.24. So remember, this is my point of estimate. All right, so that's your point of estimate. So now what we're going to go ahead and do, we're going to go ahead and calculate standard error, and then we're going to calculate margin of error. So we get standard error, which is square root of p hat times 1 minus p hat, all divided by n. So I'm going to say square root of p hat, which is 0.24 times 1 minus 0.24, and you divide this by n. N in this case is 500. Any question on how I got square root of 0.24 times 1 minus 0.24 divided by 500? All right, so I'm going to go ahead and do this in my calculator. So we'll do second. We'll say we'll say x squared. We'll say 0.24. And remember, you always want to do the 1 minus part kind of either mentally or prior to it. Okay, you don't really want to be dealing with parentheses. So if you do 1 minus 0.24, you get 0.76. So you get 0.76. And you divide this by 500. And you press enter. So you get 0.0191. And you usually get 4 decimal places just to kind of keep it somewhat accurate. Any question for the standard error? So up next, we're gonna go ahead and do is we're gonna go ahead and do the margin of error. So to do the margin of error, if you remember margin of error, which I label as n, is equal to z alpha divided by 2 multiplied by p half of 1 minus p half all divided by n. So if you remember for this one, what did I say z alpha divided by 2 was equal to? Well, that was the alpha divided by 2. But what is z alpha divided by 2 equal to? There you go. Z alpha divided by 2 is equal to 2.576. That's what your z value is equal to. Because remember, the 0.01 divided by 2, we use that in order to get the z value. But once you get the z value, pretty much you say z alpha divided by 2 is equal to whatever you got in the inverse norm. All right, so then you multiply by what we got for standard error. We got standard error is 0.0191. Any question? I got 2.576 multiplied by 0.0191. Okay, so I'm gonna go ahead and just multiply that. So 2.576 multiplied by 0.0191. So if you do that, you get 0.0492. So this is what we call our margin of error. So if we're talking about this margin of error in percent, how much percent do we have as a margin of error? Oh, you want to check that again? There you go. So this is a 4.9% margin of error. So if you ever look like an election day, yeah, it's fine. If you ever look like an election day, they'll say like how many, well, what percentage of people have voted for some candidate? And then they'll say a plus or minus like 5%. So that plus or minus 5% or whatever they're giving it is the margin of error. So it's telling you how much the swing vote could be. So it's saying it could either be that, say, they say 52% with a plus or minus 5%. It could either mean that 57% of the people voted for that candidate, or it could be that if you do 52 minus that 5%, it will be that 47% of the people voted for that candidate. Which part do you get lost on? So if you ever look at the news in the election day, they'll always have that where they tell you like how many people have, well, the percentage of people who have voted for that candidate. And they'll also just say like, this is a margin of error because they're telling you, okay, not everybody have voted. So this is how much it could essentially jump by. All right, so last thing we're gonna do, we're gonna get the margin of error and we're gonna get the point of estimate. So we're gonna get the margin of error and we're gonna get the point of estimate. Because if you remember for the final part for it, you get p hat plus or minus my margin of error. So for this one, we get p hat, which is 0.24. And we say plus or minus my margin of error, which is 0.0492. All right. So we get 0.24, because that's my point of estimate, and we add and subtract it to my margin of error, which in this case is 0.0492. So let me go over to my calculator, for that I can show you how to do this. All right, so you do 0.24 minus 0.0492. So we get 0.1908. So we do this again. All we do is change the negative to a positive. Now we go 0.2892. All right, and that's our confidence interval. So our confidence interval is anywhere from 19% all the way to roughly 29%. So let me show you how I wrote it down on my notes. So if you look at it, I put this one in the lower half. If you look at this one, I put this in the upper half. So one thing you have to know, the confidence interval always go, the smaller number go on the left-hand side, the bigger number go on the right-hand side. So if you look at this confidence interval, telling us our parameter could be anywhere from 19% to 29%. So essentially that's the range that it's giving us for our parameter. And that's how you find the confidence interval. Any question on how I found this confidence interval? All right, so the reason why, if you look over that, all right, so we're completely done with this problem. I'm just gonna go back to why for the z value is always positive. So let's do a study color, let's do blue. So say if I would have said this is negative, so that means this would have been negative, and now this would have been negative, correct? All right, cool, thank you. So that means this value would have been negative, correct? So then that margin error will also be negative, correct? So if I do 0.24 plus a negative 0.0492, or if I do 0.24 minus a negative 0.0492, would that change my answer at all? Well, it's not going to change your answer at all, because if you look right here, you have a positive and a negative. If you do positive times a negative yeah, will just give you a negative. Or what about right here? If I do a negative times a negative times a negative will give us what? It will give you a positive, correct though. So if you look at it, you end up back with just positive and negative. So that way for the z value, that's why we always put it as a negative. Well, sorry, that's why we always put it as a positive, because we know since we're going to do the positive and the negative is not going to change anything. Like you're still going to get your same answer. So that way it's much easier. Always put it as a positive. All right, cool. Glad it makes sense. All right, so what I'm gonna do, I'm also gonna show you how to double check your answer using the calculator. So, so for your calculator, all you literally need is X, N, and 99%. So let's go to the calculator. So in your calculator, what you wanna go ahead, you wanna go right here where it says stats. You wanna go where it says tests. So let me show you again, in case you got lost. So you wanna go to the stats button. You wanna move it over where it says tests. And for this one, what you wanna do, you wanna go where it says number 5. If you look at it, it says one prop, oh, sorry, not number 5, Has to go a little bit lower. All right, so you wanna go to letter A. So you wanna go to letter A where it says one prop. Prop mean for proportion. And then if you look at how it says z int mean interval. So this is gonna give you the pretty much your confidence interval. So you wanna press this one. So if you look at it, here go my X value. So my X value in this case is 120 my N is 500. And then you want to put confidence level. For confidence level, for this one, you can either put it at the percent or at the decimal. It actually make no difference. They'll give you the correct answer. So let's put 99%. Let's go to calculate. Oh, and we're done. So if you look at the answer that we got from the calculator, we got that at 0.1908. That's my lower bound. And if you look from my upper bound, it's 0.2892. So it gave us exactly what we got from doing it by hand. And that's how you double check your answer using the calculator. All right. Any question on the process of the calculator? All right, so I think I can fit in one more problem and then that will be it for today. Well, let me look at the problem. Yeah, actually, we'll just leave this for Monday. All right, so yes. Okay, so let's stop here. All right, cool. Yeah, so what we're gonna do, we're gonna stop right here. So if you look at it, we already have 7 quizzes. So the next quiz is gonna be your last quiz. And then after that, pretty much all of your lower quiz are gonna start dropping if you start doing better than your lowest quiz. So after the 8th quiz, your quiz score technically could only go up as long as you do better than one of your worst quiz. So for the quizzes, pretty much we're almost at the 8 mark. Also for your test, you're gonna have a test on chapter 7, 8, and 9. It's not gonna be this Monday, it's gonna be the following Monday. Here, let me get the date for that. So that way, if you're kind of planning something, all right. So the test will be July. I think Stephanie already got it for me. Yeah, 27th. So test number 3 will be on July 27th, and that's going to cover chapter 7, 8, and 9. So that's what chapter, well, that's, ooh, here. I accidentally sent it to one person versus the whole class. July 27th. All right, so your third exam will be on July 27th, and it's going to cover that. Well, no, Tuesday is not the last quiz. Tuesday is going to be pretty much your 8th quiz. And then after that, then any quiz they do better than, in like say quiz number 9, you do better than one of your last quizzes or one of your lowest quizzes, I'm going to start dropping quizzes. So next Tuesday is not the final quiz. It is saying like after next Tuesday, any quiz they do better than a previous quiz is going to be dropped. And also for test correction is due on Wednesday. So if I were you, I would get the test correction done most likely this weekend. So that way you can start focusing on your test 3. Because test 3, like you do want to focus on that one. All right. Any questions about anything before I close this up? Yeah, Wednesday is your test correction for test 2. All right, cool. All right, so since there's no question, I'll close out this meeting. I'll upload the notes for chapter 8 and chapter 9 in case you missed something. I'll also upload the notes on, well, I'll upload the lecture on Canvas. All right, guys, have a good weekend. I'll see you next Monday.